Hi, I'm Rodney, and I'm here to tell you that finding optimal corner solutions in domino reduction is a solved problem, and I'm going to explain how. Not using any giant algorithm sets, Hyper-Parity is a way of analyzing your corners and finding the most direct route to bringing those corners from any starting state to half-turn reduction. Talking linear solutions, no trial and error, no backtracking. If you don't know what I'm talking about, you might as well stop watching because I'm not going to fill in the background. But if you're an FMCer who sometimes doesn't know how to proceed when you hit a DR case with bad corners, then check it out.
If I'm in domino reduction and trying to solve the corners, a necessary first step is for me to get them into half-turn reduction, HTR. For that to be the case, a few things have to happen. It's not enough for me to bring all the U stickers onto the same face, as in this example, because I still need my front and back faces to only be showing blue and green stickers. It's not enough just to solve those. In this example, I've now put the blue-green stickers only on the front back faces, but now my UD stickers are no longer solvable using half turns. And even if I manage to do both of them together, that would be something like this. Now I have my UD stickers all together. I have my front back face only showing blue-green stickers for the corners, but I am still not solved because what I'm missing in order to fully solve the cube is a corner swap. So the reason this is not in HTR is because of parity, which is a familiar concept in cubing. Parity is the number of pairwise swaps you need to execute to solve the cube. It's either even or odd, and in this case it's odd because it's 1. When you do a quarter turn, any UD turn will execute 3 pairwise swaps, and so if your parity is odd, that means you need an odd number of quarter turns to get to HTR. What I'm going to do in this method is also describe the orientation of the UD stickers and the FB stickers in terms of how many quarter turns are required to bring them into HTR. That's the inspiration behind the term hyper-parity.
First thing I'm going to do is look at all the different ways in which the UD stickers can be distributed. So there are 4 yellow stickers. They can obviously be split 4-0 or 3-1 or 2-2. And if they're split 2-1 or 2-2 or 3-1, then they can make different patterns. But I'm going to group all the patterns according to how many quarter turns are required to solve the corners. So here I have 4-0, they're solved. This I'm also putting in the same group because it's 0 quarter turns away from being solved. I can solve it with just a half turn. The other way that I can that's in the same group is this configuration where the yellows are in this slash. These in this slash, all right, diagonals on top where they're parallel. These are all 0 quarter turns from being solved. But if I make a quarter turn in each of these configurations, I end up in somewhere different. So if I make a quarter turn from here, I'm 1 quarter turn away from being solved, and this is recognizable because I still have the diagonals, but now the diagonals are in this cross pattern. There's only one member of this group, no matter what half turns I do. I have the same pattern for yellow stickers, so a quarter turn brings me back to solved. But if I now arrange my yellow stickers such that they're split 2-2 and do a quarter turn, now I have a new configuration. And this is, again, also one quarter turn away from being solved. My yellows are in this pattern.
That's if the UD stickers are split 2-2. If they're split 3-1, there will be one face that has exactly 1 yellow sticker, one face that has exactly 1 white sticker. So you look at the solo yellow and the solo white and how they're arranged relative to each other. So if they're spaced by a diagonal, then you are one quarter turn away from solved. After a quarter turn, you can bring them so that they are positioned vertically relative to another, and then you are 2 quarter turns from being solved.
If I bring the yellow stickers so that they're split 2-2, now the pattern that they make is a bar and a diagonal, so this bar slash, and that's the only possibility, because if I make a quarter turn from here, I stay in the bar slash positions. I have 2-2 split, or I have 3-1 split. Now I can get back to solve by making the quarter turn when I have the 3-1 split, going back to 2-2. Now there's my bars, and then I align them and unsolved. Now I'm going to do the same kind of analysis for the side stickers. So for the side stickers, I'm completely ignoring the difference between red and orange. I'm ignoring the difference between blue and green. What I'm counting are the bad corners. So in the solved state, there are 0 bad corners. A bad corner means a red sticker on the front or back face. So starting out, I have 0 bad corners. So there's only one possibility. A U move gets me to 4 bad corners, and the 4 bad corners are all on the same face. But there are 3 different members of this group, because those 4 corners can be split 4-0 or 2-2. If I split them 2-2 this way, so this is the diagonal that we saw before, now a U-turn actually keeps me in the same state. So I still have these 2 diagonal bad corners after a U-turn if they're in this configuration. If they're in this configuration, those are my bad corners now, then a U-turn gets me to this configuration. This is now 2 turns away from being solved. My bad corners look like this. This is a familiar pattern. Bad corners look like this when they're split 2-2. That's 2 and 2. I can make my bad corners split 3-1, 1 and 3. And now a quarter turn gets me to a new state. And that is a state with only two bad corners. Everything else is good. And of course, if I have 6 bad corners, it's the same. It's just I did a rotation. So 6 bad corners, 2 bad corners are equivalent. And those 2 bad corners can be split 1-1 or 2-0. If I split them 2-0, then a quarter turn does nothing. Quarter turn, I still have two bad corners, and so we're done. This is 3 quarter turns away from solved. That's the most we can be away from solved for the side stickers. To get back to solved, I have to split up the bad corners, do a turn. Now I have 4 bad corners again. I put them in the bar situation. Now I'm 2 away. Now I'm 1 away. Bring the bars to the same face. Quarter turn, and my side stickers are solved.
So now I've grouped all possible UD sticker configurations into 4 groups that are either 0, 1, or 2 quarter turns from solved. I've grouped all possible FB sticker configurations, side sticker configurations, into 4 groups that is 0, 1, 2, or 3 quarter turns away from being solved. So that means that the entire universe of DR corner states is describable by those 2 numbers plus parity. So 4 states times 4 states, that would be 16. It turns out that there's actually 17 because some of those combinations are not achievable and some can be combined in a couple different ways, and I'll go over that. But there's basically 1, 2, 3 states that cannot be formed. There's 1, 2 states that have a good and a bad configuration, and there's 1 state that has a good, a bad, and a really bad combination. So 17 possible sticker configurations times 2 parity states. That's all the possibilities.
Let's take a look at this case in some detail. So this is a case where my UD stickers are in this bar configuration like that. So that's 1 quarter turn needed to solve the UD stickers. My FB stickers have 2 bad ones, only 2. So that means I'm 3 away from solving the FB faces. Does that mean I can solve the whole cube in 3 quarter turns? Not necessarily. Depends on what my parity is. So I'm going to count corner cycles to count the parity. This is a 1, 2, 3, 4. A 4 cycle, so that's 3 swaps. And then I have 1, 2, so that's 1 more swap. So that's 4 swaps total. That's an even number. That means I need an even number of quarter turns. I can't do it in 2 because this requires 3, so I'm going to need 4 quarter turns to solve the corners. So let's look at the possibilities for where the first quarter turn can get us. There are 2 ways that the FB stickers can be arranged. These can be split 2-0 or 1-1, and the UD stickers can similarly be split 2-2 or 3-1. So that's going to be 4 possibilities. So first quarter turn like this keeps me with 2 bad FB edges, so that's going to be that's going to remain 3 turns away from being solved, and my UD stickers have gone to solved, so that's one possibility. If I split the UD stickers 3-1, then my UD stickers are going to go from 1 away to 2 away, and I'm going to stay 3 away for the FB stickers. So that's the other possibility. That's number 2. Number 3 is if I split these bad FB stickers, UD stickers 1-1, so that's going to go to 2 and 2. And then the other possibility is I split the red stickers, but I have the UD stickers split 2-2, so then I'm going to go to solved for UD stickers and 2 away for the front back stickers. So here we have the 4 possibilities for where I can go after 1 quarter turn from this state. Actually, only 2 of them are useful if I'm trying to solve in 4 quarter turns, because 2 of them cannot be solved in 3 quarter turns. And so that's good information. I can eliminate those 2, and I can only consider these two possibilities. But of course, to know that, I have to actually know how all of these different points in the grid can possibly connect to one another, and that's the point of the next section. So now we're going to map out all the possible transitions in this grid, and we're going to do it breadth first. So that means I'm starting from the solved state, and I'm going to find all the cases that are 1 quarter turned away from being solved. And there are 3. This is the first one. The second one is this. And the third one is this. Continuing on, we're going to find all the HTR minus 2 quarter turn states by starting from all of the HTR minus 1 quarter turn state and looking for all the possibilities. So starting from this configuration, there's 2 possibilities. This is the first one, and this is the second one. Now, the second one I've already seen from the 1 quarter turn configuration. I can actually bring it to what looks like solved.
But my parity is now odd because I took 3 quarter turns to get back to this state.
Starting from this state, there's only 1 possibility, and it's this. Starting from this state, there are 2 possibilities. This is 1, and the other is this one. Now I'm in a state where the UD stickers are solved and the FB stickers are 1 quarter turn away from solved, but this is different from the way I reached this state before, which you can see if you actually bring all the FB stickers to the top face. You'll see that I don't have all the whites on the top, which means I can't solve it. Can't solve the FB stickers while keeping the UD stickers solved. So this is the bad way of combining those 2 UD and FB states. Continuing on now, we're going to find all the states that are 3 quarter turns from HTR, starting with the ones that are 2 from away. Starting from this state, there are 2 possibilities. One is this, and the other is this. Continuing from this state, there are 2 possibilities. This is the first one, and the second one is that. 3 additional possibilities from here. They are 1, second one is this one, and the third one is this one. And this looks like a state we've seen before, but again, it's put together in a different way. If you look at the bad side corners, you'll see here they all have the same color. They're all yellow. In the previous one, the bad corners were split 2 yellow and 2 white. From this state, there are also 3 possibilities. This is the first one. This is the second one. And the third one is here.
Marching on, you'll be thrilled to hear that we're more than halfway through. We are now solidly out of the region of what anyone would consider easy corner cases. I'm going to now start with everything that is HTR-3 and find the remaining possibilities. So here's the first state. It has 2 possibilities we haven't seen yet. That's the first one. That's the second one. This state has only 1 possibility. This is the bad version of the UD1-2 state. It has 1 possibility, which is we haven't seen before, and that's this, which is actually leads us to the bad version of the 2-3 state. This is one of those states that looks like HTR but isn't. It has a connection that we haven't seen yet, which is split those yellows 3-1 and go to there. From here, we can continue by splitting the reds. Quarter turn brings us now to this. This is now the third and worst combination of the UD1 FP2 configuration. We can also split the red stickers this way and do a quarter turn that ends us back, that goes back to itself. And lastly, we have this 2-3 configuration. This is the good version, and then a quarter turn brings me to the bad version. We are so close to done. We uncovered 3 new states in the last round, so let's see where they lead to. This first one leads over to here. I can also split the yellows 2-2, and then it leads back to itself. This state also connects back to that same one, and it also has the possibility of connecting to itself. And that is it.
So here we have it. This diagram represents all the possible DR corner states and all the ways in which you can get from one to another. Remember when I was talking about this state and there were 4 possible transitions that I could execute with a quarter move. 2 of them were not useful for the even parity case because it couldn't be solved in 3 moves. That was this one. This one cannot be solved in 3 quarter turns. One, it takes at least 4. This one also cannot be solved in 3 quarter turns. It can be solved in 2, but not 3. So if you're in a scramble and you're in the state, parity is even, you can form some pairs, form some pairs, try this U-turn, maybe you can form some more pairs and go here, maybe you can form some more pairs and go here, try the inverse, whatever. You can also do the same thing, form some pairs, go to this one, see if you can form more pairs, etc. And that's how you can find good skeletons for any corner case. This is a complicated diagram, I'll grant you that, but if you were to try to represent this as an algorithm list, there'd be probably 100 algorithms in there, because each path through here is an algorithm that you would have to write down as a possible corner solution for this state. Your brain is much better at retaining the information, this spatial geometric information in a diagram like this. I call it the Hyper-Parity maze. Print it out, trace the paths with your finger, see how the connections go. The shape will pretty soon become apparent to you. If you wanted to prioritize, the most common states are kind of down in this corner. These are the ones that come most often from a random scramble. So if you were able to learn to recognize the difference between these 2, between these 2, between these 3, and learn the even and odd parity solutions for these cases, you would be well on your way to solving the majority of domino scrambles with no trial and error. Now I'll close this out by returning to the case we were looking at before, where the UD stickers require 1/4 turn and the FB stickers require 3/4 turns, starting from the odd parity case, which is the easier one.
So there are two ways to solve that. The first one is like this. You split the reds, let the yellows be 3/1, 1/4 turn, split the yellows 3/1 again, and solved. The second way to solve this configuration with odd parity is by taking this path. That's split the reds while making the yellows split 2/2, 1/4 turn, yellows into slashes, 1/4 turn, and solved. Now for the even parity case, there are 4 solutions. First one looks like this. Go down, split the reds, 2/2. Yellows, you need to be 3/1, so that's not right. That's the one I want. And that's solved. Second solution starts off the same. Keep these together. But this time I want to split them while the yellows are 3/1. So that's this way. Now, when I bring these together, I have to make sure that I'm in the good configuration. That means these yellows are going to match up with that. That is where I am, and so there I'm solved. Next two solutions start by going up and to the left. So that means splitting the reds while the yellows are 2/2. So there's like that. This solution goes slashes. I need to do one like that, and then solved. The second solution starts out the same way, but this time I actually solve the UD corners. Retain like that, and we are done.
So there you have it, linear generation of corner skeletons in domino reduction. I've tested this over hundreds and hundreds of DR scrambles, and here are the patterns I've noticed. First, the optimal move count to fully solve the cube, corners and edges, is almost always 13 or 14. Doesn't matter if the corners are good or bad. 12s are uncommon, 11s are rare, 15s are rare. But the median move count for the 2/4 turn corner case is about the same as the median move count for the 4/4 turn corner case. So learn the recognition, learn the maze, and you don't have to discount those possibilities. It doesn't hurt you that it takes more moves to solve the corners, because as you solve the corners, you can be solving edges too. I think there's more to be done here, but the familiar techniques will work. That's forming pairs, preserving pairs, switching to inverse, inserting edge commutators. So if you decide to give this a try, let me know how it goes, and have fun.